So in the exam, this problem was there. You did that?
The
First one, yeah.
part B.
Part B was one, okay. So maybe I will not recall. Maybe who haven't done here, he can.
I mean, I talked to him, he just didn't know the
Exactly.
probability this like
Yeah,
density.
it is just that you have a state rho, then you have two random variables, xi eta, which follows normal. I mean the multivariate normal with CD as the covariance mean and the covariance sigma, which is 2n cross 2n matrix. Then you define a new state rho, call it rho naught, then rho equal to the W of xi plus I eta. This is a random state, of course. This is a random state as it is. Okay. W of xi plus I eta star. This will be a random state. But then to make it a state, you take the expectation. Okay? Expectation of this, whatever it means. So, but then you are taking, this is an operator valued random variable. It looks like an operator valued random variable. And then you have to take the expectation. You don't have to do all that. Yeah, you have to find the characteristic function. Now rho hat is going to be, suppose direct sum, rho hat is going to be the trace of rho W of Z, rho hat of Z. Rho hat of Z is going to be W of Z. Now, if you know the basic trick, and if you use that W, you will get the W of xi plus I eta rho naught there, and you can take it to the other side using tracial property, and you will get rho of W of Z times some scalar. Okay, you have the E here, let it be. Then you have the scalar, which is just e power minus 2i or plus 2i. I'm not sure, imaginary part of. So there may be a root 2 involved in that. If you go through that, but depending upon what you actually use, rho g or whatever, it doesn't matter. Okay. So as far as we understand it correctly, it doesn't matter. So imaginary part of that xi plus I eta and z. Maybe this way or that way, I don't know. There may be a flip, I don't know. Okay, we can think about that. That doesn't matter. The point is, yeah. So you only have these are all just, non-random. It's not random. Okay. So only that part is a random, which is a scalar, and you are taking expectation. Expectation is integration basically, which is just a finitely linear sum. It's a limit of linear sum, and trace is linear and it's also continuous. So you can take everything out. Okay. So it is just going to be expectation. It is just going to be, so the other one is just rho hat, rho naught. This is rho naught. So rho naught hat of Z times expectation of that scalar, whatever. But that is just the characteristic function with something else there. Characteristic function acting on something else there, where Z is the variable there and xi plus I eta is the random variable. It is a characteristic function of that, which will be given by Gaussian. But you have to be careful because there is imaginary, it's not the inner product. Usually in the characteristic function, it will be given by the inner product. But here you have imaginary part, so you have to apply J. So that will give that you will get a new characteristic function where the mean will add up and the covariance matrix will also add up, but there will be a conjugation by J. Okay, that's all. So that's what. Okay. So let me not write the whole thing. Can submit as assignment.
Okay.
If you have done it, you don't.
Very nice. No, when I was doing, I took the trace and expectation, I switched, and then I integrated the characteristic function itself.
Yeah.
That is just messier. But
but that is actually a characteristic function of Gaussian. So you immediately get it. Okay. So you know the mean, you know the covariance of that. There is actually, maybe there is a number. I don't know, whatever. Okay. So you get it. That's all. So this is also a channel. This is what is called bosonic channel. This rho hat going to this W of xi plus I eta, rho W of xi plus xi plus I eta star expectation This is what is also given a two classical random variable or given a 2n valued or 2n valued classical random variable. You can get a map. You can get a complete. This is a completely positive map. You will come to the proof later. I mean, we will. I mean, this can be actually written as this is T of rho hat is equal to this. Okay, the T is a completely positive map. You can actually write it as this T of rho hat equal to summation some Vi rho hat Vi star. Okay, for some Vi. Okay, that means it's a finite sum. That means it is a completely positive map. In fact, every completely positive map will look like this, where the summation may be infinite, and you have to make sense of that infinite. I mean, make sense of that limit in the right topology, and that's what we are going to do in this class. After another example. Okay, so what we were doing in the last class is what is called symplectic channel, right? Symplectic channel. So symplectic channel is you amplify, you take a state, amplify to a bigger Hilbert space by tensoring with another standard state. But you can just tensor it with just a vacuum state, because any state can be written as, I mean, any state can be purified, maybe by further amplification. And any pure state, I mean, any state can be purified, and any pure state is actually gamma of L acting on, I mean, if you want it to be mean zero, gamma of L acting on the vacuum state. Because of that, you have the T of rho equal to rho tensor. You just amplify with the vacuum state. Okay. And then apply gamma of L star, gamma of L. These are all completely positive maps, and then take the trace 2. And trace 2, I mean, back to the original Hilbert space. So L2 of Rn or something. So where L is in SP 2n plus 2m. Okay. And this E0 is in L2 of Rm. Okay. L2 of Rm. This is a vacuum vector in L2 of Rm. So it's well defined. Okay, trace 2 is you just take the second, the Rm, L2 of Rm, you take the trace over that Hilbert space and you get this. Okay, so this is what is called symplectic channel. And we have I think we have more or less computed. I mean, I didn't write each and every detail, but it's clear. So if L inverse equal to some M11, M12, M21, M22. It's a matrix in M2n plus M R. Then this, if rho is equal to rho G, it's a Gaussian random variable with mean L plus IM and S, covariance matrix S. Then to call it TL or something, okay, I call it TL. Okay. Then TL of rho equal to rho G equal to rho G some L prime M prime S prime, where L prime M prime equal to that M11 acting on LM. That's all. And S prime equal to M11 transpose S M11 plus half. You will get somewhere the identity. When you will get when you tensor with that, you will get half identity. I mean, the vacuum state, no? That adds an half identity, which when you multiply with gamma L, you will get it here. Okay. So when you conjugate with gamma L, you will get that half that. But then since this L inverse is acting, when you are conjugating with gamma L inverse, so you get this half of M21 M21. So this is what. So you can just add an arbitrary matrix, and you can add an arbitrary. You can do this. Okay. So This is what a symplectic channel is. Okay. Now the following proposition, which is just some nice property. Okay, if L is in SP2n plus 2, first I want to apply, doesn't matter, 2L, let it be. And M is in SP2n plus 2M. Okay. Then there exists a N in SP2M such that EL, TM, when you compose these two operators, it is just TM. That's all. So you can compose two symplectic thing, but then you can, it will not be just matrix multiplication. You have to multiply in by suitable amplification. You have to do an amplification and then multiply. It is exactly that proof. But the point is you have to do it for the inverse, right? See, because it is the inverse which is acting there. So you have to do the inverse. So let L is equal to L11, L inverse equal to L11, L12, L21, L22, and M inverse equal to M11, M12, M21, M22. Okay. Then we can define a new matrix L tilde. I mean this is not L tilde inverse. I mean, if I put an inverse, it will look like L inverse tilde. I mean, inverse of L tilde, but I want to just amplify this L inverse. Okay. Let me write L tilde itself. Doesn't matter. Okay, please understand. I mean, it's not the L is amplified, it is L inverse is amplified. Okay. Just not to complicate, I just write it like this. So, which is just L12, L21, L22. And then you add zeros everywhere and identity here. Identity. But this identity is 2M, right? 2M identity. L should be done or M should be done. But I want to add to M. Okay. And M inverse and M tilde equal to M11. But I put the zero in a different place. I mean, these are all block matrices, okay, of the right size. Okay? Whatever the right size is. This will be, I mean, the top one, L is just 2N plus 2L size matrix. And so the right block matrix you have to remember. And here it should be 0. Here I have the identity here. Identity 2L, 0, and M21, M12, M22, 0. So I have amplified like this. Now you multiply. So first I want to apply M and then L. So here it should be the inverse should be multiplied M and L. Okay. So N tilde equal to N tilde equal to M tilde L tilde. And the N is N tilde inverse. Okay. The N is N tilde inverse. Right. Now let us just, I mean, now it's clear. You just multiply. So M tilde, N tilde equal to what? I don't have to calculate each and every entry. I don't have to calculate each and every entry. I just have to calculate the 1/1 and this first block row, first column, block column, or the column block, whatever. So M and L tilde I have to write. So if you multiply, you will get M11, L11, right? Okay. And here it doesn't matter. I am not writing it. So here, this block, it's going to be second row, I2L, L21, right? So I2L with respect to this vector. Third one, M12. 2 No, here, this one, M21 multiplied with L11, right? Yeah. M21, the last one is 0. So M21 multiplied with L11, right? So whatever I have here doesn't matter.
So the second one should be L22.
Yeah, second one is you take the second row and multiply with this L2, right? L21.
Yeah.
L21. So last one, yeah, L1. So okay, so this is what I get. So, and of course, this is just the you amplify this. That is clearly you add a direct sum. You add a direct sum that is symplectic, and you count. So L tilde, M tilde, they are symplectic. You multiply them, that is symplectic. You take the inverse, that is symplectic. So N is symplectic. Okay. So we have to verify that T. Now we have to verify that what is T N tilde. Okay. And we have to verify that that is the composition we want to see. So T N tilde, because N is the, I mean, N is equal to N tilde inverse. So T N tilde of that original. So G L M S is going to be, of course, is going to be rho G L M another S prime L prime, where L prime M prime is going to be M11 L11. Here it doesn't matter. It's clear. This just the composition is clear now here. Okay, which will be the first entry of that N tilde, right? Of LM. Okay. On the other hand, S prime is going to be, you have to take this first row, M11, L11 transpose, S and M11, L11, L11, plus half of whatever we have here. This thing, right? This thing transpose times this, right? That is going to be L21 transpose L21 plus M21 L11 transpose M21 L11. Right. That's all. I have just returned the T N tilde, whatever it does for the S prime. Okay. Now that is going to be, that is equal to, so what does it do? I have M11 L11. Here M21 L11 here. So this is okay. And in the middle, I will get L11, L11, L11 transpose. Yeah. So I have this L11 transpose is come out, right? So L11 transpose in the middle, M11 transpose M11. Okay, that's what the first term is. I mean, I will get the plus half of M21 transpose M21 times LL1, right? Plus half of L21 transpose L21. Right? Now, this is the new covariance matrix when you act the TM. Right? That is a new covariance matrix when you act TM. Then you are acting, then you call that as some S double prime or whatever. Then you are applying TL, you get this. Okay. So it's clear that Tn. So this is what we calculated Tn, which is this covariance. I mean, the mean it's direct. There is nothing. M11, L11, mean is direct. That's nothing. So Tnn is equal to TL and Tm. Okay. So we have proved this. This also says there is a corollary. I mean, this is what is, and this happens. I mean, I see this. This says that if L has a symplectic dilation of 2n plus 2m, M has 2n symplectic dilation of 2. I mean, M has symplectic dilation of 2n plus 2m, L has symplectic dilation of 2n plus 2L, then we have the product L times M, not the product. This is not, sorry, what I'm saying is nonsense. If A has symplectic dilation, it's about matrices, okay? Symplectic dilation. This proof dilation of order 2L plus 2n, and B has symplectic dilation of order 2n plus 2L, okay? Then AB has a symplectic dilation of order 2n plus 2m plus 2L. Just clear whatever we have produced with that proof.
AB as in like the product of.
Just the product of AB. A and B are in, I mean, these are all in M, 2n. You have some matrices AB, 2n cross 2n matrices. Then, I mean, we already know that, but just this is just a statement about order. You know, every matrix has a symplectic dilation. This is just about the order. So this order. So this is the color. Okay. So after this, in KRP books, he discusses some very important channel, and which is given by two matrices, A and B, satisfying some conditions for it to be completely positive. And so see, the idea is following. So a channel channel is a completely positive map, and it takes state to state. That's what we are working on. As I said, there is a dual picture. I mean, there is a, you can define the the completely positive map can be on B of H. You can consider it on trace class operators on B of H. But if you want to define any map on B of H, if you want to see B of L2 Rn, which is a Fock space, of course, P of gamma of Cn. Okay. We know that this is generated by this W of Z, where Z is in Cn. Okay. Then you take the strong topology. Okay. This is equal to that. This is the linear span, of course. You need to take the span. You take the linear span, which is same as the algebra generated by that because of the canonical commutation relation. So you take the span of W of Z, and of course, if you close it in the norm topology, you will not get much. I mean, you will get a C-star algebra. That is what is called CCR algebra or something. You do get a nice algebra, which is called CCR algebra.
The span of real operators.
No, span of? Just no, take the span, close it in a norm topology.
Okay. Yeah.
That is what is called CCR algebra, which is a universal algebra satisfying some relation. I mean, universal C-star algebra. This is just a concrete example. In C-star algebra theory, there are things like that. You can abstractly you can work with C-star algebra, which is if you know the generator and satisfy some commutation relation, then there is only one C-star algebra you can generate. Okay. I mean, this is a concrete realization on some BFH. C-star algebra is an abstract object.
Yeah.
You can only by using there is something called GNS construction, you can always embed it in BFH, but it can be just some anything.
Yeah.
Okay. So this is what I call CCR algebra, whatever CCR of order, whatever n or something. Okay. That will be just a C-star algebra if you take the norm. Okay. But if you close it in the strong topology, you get everything. You have that. Okay. Which is banana algebra. So you need to take the strong topology. So if we want to define any map on B of L2 of Rn, maybe it's a CP map, completely positive map, or it's a homomorphism, endomorphism, whatever we call it, endomorphism. You can define it on W of Z and extend it linearly to the algebra generated by that. Then you have to see whether it extends to the whole space.
Yeah.
Okay.
But that map will only be like strongly continuous.
Yeah, the map has to be strongly continuous. Then only you can.
Like it won't be like it won't be uniformly continuous.
It will be, I mean, you can extend to the closure also, C-star algebra also. Strong continuous is much more than that. Right?
But yeah, strong closure is weaker.
Xn converges X in strong topology. Then Xn will converge in weak topology. So if it is weakly continuous, it will converge in the weak topology. Okay. In for Hilbert space, weak continuity is same as norm continuity for some reason.
Okay.
Because of closed graph theorem.
Okay.
Here,
No, yeah. In
yeah, here it
weak
will
continuous implies strongly continuous in Hilbert space.
Hilbert space, but here it will not be the case. Actually, it will be no. The map will be norm-continuous, but then you will want to put some semi-group property, and there the semi-group will not be norm-continuous. It will be weak continuous or something. Anyway, so the idea is you want to define it on these Weyl operators, then you want to extend it. You want to see whether it is strongly continuous to extend it. So that is not always easy to prove. That's a non-trivial part. Okay. So here he defines some CP map in KRP's paper. I didn't see a proof of why it extends to the whole of them. It's defined on these Weyl operators. Then you have to extend to the whole of big space. So I will do it later. I will try to get a proof somewhere. I'll try to get a proof somehow. Okay. Then we will.
Like, what's the map?
The map is something like I have to remember. You need two matrices. You apply a scalar. I mean, this is just W of Z. Vaguely, I have to remember. I didn't. You will apply a BZ. You will get a. Okay. Then you will have a scalar part here, e power something. Okay. And there we will have another matrix, A or something. This A and B will have some relation. Okay. I don't know exactly that. Some half of A something. Okay. There are very nice maps. For example, if you take any.
How do you prove complete positivity in general? Like for finite dimensions, we have the Choikra operators.
You can tensor it and then you will.
Like, is there a like the Choikra decomposition for infinite dimensions?
So that's what we will prove now. Okay, we will try to prove now. I said that some will be infinite. So
that's it. Everything else is the same.
Of course, infinity means you need strong topology or something. Okay, so okay. So that's what we want to do. So we want to do some complete theory of completely positive maps. Okay, then we will come back to that. We will quickly do that. Okay. So we know what is a completely positive map. Let me just recall T from B of H1. We are not dealing with any fundamental algebra. We are dealing with only B of H. Okay, for the time being. B of H2. B of H2 okay, is CP if T. I mean, it's positive. So let me. So formally, let me define. We have already defined. Let me say, is positive if T of any positive element is positive. B of H1 or T or X or something. I mean, for C-star algebra, I will write X over here out X. Okay. Okay. So it's T is completely positive. Positive if one tensor T, which you can write it from Mn tensor B of H1 to Mn tensor B of H2 is positive for all n. That is what. If it is for positive for n, for any n, that's called n positive. If it is positive for all n, that is what is called completely positive. We should remember that what is this one tensor T? So this Mn tensor, MNC tensor B of H1 is nothing but M, which is same as Mn of B of H, matrix with entries coming from B of H, which is also equal to B of H, Cn tensor H. Okay. Cn tensor H, or it is same as we can have all this identification. H direct sum H n times. It is just the okay. So it is just the n cross n matrices with entries there. So one tensor T acting on any Xij, where Xij is coming from B of H1, okay, is going to be just T of Xij. That's all. Pointwise. Okay, that's all. So this is the one tensor T, and this map has to be positive for all n. This is not automatic in non-commutative setup. Okay. Okay. Even for finite dimension. Okay, it's not. You'll see examples later. So we want to get a nice form of this. For that, we want to do, say, we want to get what is called Stein spring representation. We want to associate a endomorphism corresponding to this, or a homomorphism corresponding to this, not endomorphism, homomorphism corresponding to that, so that we will dilate the CP map to the homomorphism and bring it down. Okay. So, I mean, we will amplify this H1, and then we will get a homomorphism to the bigger space, so that when you cut it down by an isometry or something, if it is unital, that will be isometry. Cut it down by isometry, you will get this original CP map. We'll write down all the details. Okay. Okay. To do that, what we will do is what is called, it's like the GNS construction. I mean, it is the same as that Kolmogorov, the dilation or whatever. It's a, you have to get a positive definite kernel and do that. But if you have looked at this GNS construction, what it's a, see, you can take a positive map, just a positive linear functional. If phi is any algebra, K is just any C-star algebra. Okay. You take it B of H if you want. Then phi from A to C is positive linear functional, just positive linear functional. Okay. Then you can define an inner product on A. Okay. Equal to phi of X star Y. I mean, we assume inner product is conjugate linear, the first variable, and the same assumption. Then you can define an inner product on A. Okay. This is not inner product. It's an inner product if phi is something called faithful. That is, if phi of X star X equals 0 implies X equal to 0. This is what is called faithful. If it is faithful, there will be an inner product. Otherwise, there will be some kernel which you quotient it out. Okay. Then you take the kernel A, and phi is equal to all those X such that phi X star X equals 0. Okay. Then A quotiented with n phi, and here it will be an inner product, and then just complete it with respect to the inner product. Okay, and call it H phi. On this H phi, you can represent this A as left multiplication. Okay, and if this phi is faithful, that is faithful, but that's not a necessary condition. That will be faithful even if phi is not faithful. Okay, so you get a nice representation. So we want to do similar thing for, actually for CP map, you can construct what is called Hilbert module, but we are not going to deal with that. But we want to get a Hilbert space similar to this. So here this is the positive definite kernel. Okay, this is exactly the positive you are using phi. You get a positive definite kernel, and I mean this is what KXY. If you want, you call it KXY and do the same thing. Okay. So we want to do that. Okay. So let us prove. Let us get a positive definite kernel and then construct a Hilbert space. Okay. T from B of H1 to B of H2 is CP. Okay. Then for X1 up to Xn in B of H1, Y1 up to Yn in B of H2, this operator, which is summation over I and j, yi star, T of xi star, xj. Okay. I mean, to prove the kernel positive definite kernel property, I'm just writing it. Okay. Then what? Then yj. Okay, yj. This is greater than or equal to 0. Okay. It's clear. Proof is clear. We just have to check. This is true for all u. For any arbitrary u n. So this will be in H2. So this is in H2, right? U has to be in H2. This map is whatever the resultant map, that is in H2. Okay. So u, so summation ij yi star T of xi star xj yj. Okay. U. This has to be positive. That's what you have to say. Okay. Now this is equal to this yi star, you can bring it here. You can bring the summation, right? Out summation I. Okay. then you can bring it here, this yi u, then this is just summation over j, summation over, no, I want to bring the, yeah, that's okay, summation over j, and here it's depends on I, okay, this is for Raj, summation I t of xi star xj and yju, okay. Now this is just the summation of the tuple, no, summation I, and you can bring the summation j out, so which will be just, yeah, this is equal to yiu, and this is just the matrix T of xi star xj. This is a matrix, right? Ij matrix. Okay. This is the ith entry of this. You act it on this y1u up to ynu. Okay. You take this, and this is the ith entry of that. Okay. You just sum over j. T xi xj is a matrix, and the ith element of that, right? I'm just saying this is just this y1u up to ynu, okay, inner product. Okay. Here it is the matrix T of xi star xj, okay, xi star xj, and here we have y1u up to ynu, okay, right? This is what is this, but then this, so this is just something, I mean, this is some vector, yn, this is some vector, okay, you call it xi or something, xi, you call it xi, right? This matrix T of some element, which I want to write it as x, where x equal to this xi xj, xi star xj. Xi star xj is a positive matrix, right? Which is just, I mean, it is in this form if you want. x1 up to xn. No, it's the other way. Oh, it's right. When I take the star, it will be that, right? It is just take the row x1 up to xn star, okay, same thing, x1 up to xn, right? That is what this matrix, you know. It's like a, it's like a rank one projection, but it's not. It's an operator way of writing, right? So this is of this form xi star xj. This is a positive matrix. You apply it on that, you can take it.
So, I mean, we need to use the complete positivity, right? So,
That's what I'm saying. This is a positive. This is in B of Mn tensor B of H1.
oh yeah, right.
This is in Mn tensor B of H1, which is a positive thing. So X is positive. So this is just like this. This is greater than.
Yeah. Like, or you could just like make two big like n cross n matrices. Like you can make one matrix which has entries xi star xj, and the other one has like the yi is on diagonal.
Ya has been swallowed. Ya is.
No, like
you want to.
No, you make these two matrices and then just like T is completely positive. So T of the x star x matrix will be positive, and then you're operating it as like A star positive element A. So that will become positive again.
Yeah. How is it different?
No, it's the same thing.
Yeah.
Yeah.
We have swallowed Y, and then we got one matrix where we apply, that is just T of X, where X is this. This is the positive matrix. Then T of X is there. And T of X, that's positive. That's completely positive. We are using the completely positive property. Then that is a good one. So that's all. So that's what we have got. Now we write the kernel. What is the second one? So let us take, I mean, kernel is a function from two set, no? K of S cross S to C, right? So that S is going to be B of H1 tensor. No tensor, cross. Right? Just set, we are taking a set. From here, I have a K. K from here to C. No, this has to be taken twice. This is a S cross S cross B of H. B of H1 cross. This is a kernel on that. Okay, so B of H2 cross H1 to C. So T is a completely positive map. T is from B of H1 to B of H2. CP map. So where K of X1, Y1, U1, comma X2, Y2, U2. Okay. This is going to be, as we have already seen, this is going to be Y1 star, T of X1 star, X2, Y2 star, Y2 acting on U2, U1. This is a number, right? Okay.
So what is the last Hilbert space in the second?
B of H1 to B of H2. B of H, this is, sorry, this is also H1, sorry. H1. Yeah. You have to take the same thing. S cross S, where S is that, that's what I said. So this is positive definite. Okay. Proof. We just have to compute this summation Ci bar Cj. Okay. K of K, capital K written. K of xi, yi, uy, x, yeah, xj, yj, uj. You have to show that this is positive, right? For any C1 up to Cn, any C1 up to Cn, any x1 up to xn, y1 up to yn, u1 up to u1, we have to show that this is positive. Okay, ij equal to 1 to n. So this is positive, we have to show. But then we can calculate it, summation over ij. We will get u2 is there, no? So ui is here. And then yi star, t of xi star, xj, and yj, and uj, right? That's what we get. Okay. We want to show this is positive. We know when those two things are equal, this is positive. Okay. Right? We have calculated this.
Yeah.
Right? Yeah. We have calculated this is positive. Okay. Where those two things are equal and summation over ij. But here we have ui and uj there. We want to get rid of it. We want to get a single u. We can add more operators if you want. So what we do is the following. This is the idea of KRPFO in this book. You just choose some operator Li from H1 to H1. Okay. Such that Li of some U and U in H. Such that Li of U equal to Ui, which is possible, of course. Right? Some operator. This is possible. Then you will get Liu here and Liu here. Liu, you can take the Li star there. Then this will become summation over ij. This will become just U. Right? And then you can take the Ca also inside. CILIYI whole star, right?
Maybe LINJ.
No, sir.
One side
Sorry, LI.
Like,
No, LJ will come here. For UJ, there will be an LJ.
yeah, okay.
I'm just saying you will get CIYILI star. This will be LI star. That will be LI there, right? LI star. Then T of same thing, XI star XJ. Okay. Then CJ. CI is, this is jth part. This is a new YJ. Okay. CILI is the new YJ. CI, YI, YJ, LJ, UJ. Okay. Sorry, U. There is no U. Okay, now with the previous thing, this is greater than by the previous level. Okay. So this is the possibility. So now we can construct a Hilbert space out of it. So that is the following Hilbert space proposition. So, but we don't want, I don't know why he has done it with, this is in KRP's book, the last section, okay, on CP map. There are developed versions of this idea for CP semi-group. There are for general Hilbert module and other things. This is a basic, this is a starting point, beginning. So I don't know why B of H1 cross H2 is taken, but we will get rid of it. We will only use B of H1 and B of H1 and B of H1 and H1. Yeah, B of the H2 is not required. Okay, so there exists a Hilbert space. There exists a Hilbert space. Okay, H. Okay, and a map lambda from B of H1 cross H1. Okay, a priori we have to assume T is a CP map. Okay, B of H1 into this H. We are making this as a Hilbert space, okay? Not Hilbert space, pre-Hilbert space. Well, it will be dense, but we will make it as a total subset basically. That's what the GNS will do. Okay. To a H, okay, with the following properties. One.
Here you're using like GNS or like,
correct, the same thing. Yeah, GNS or Kolmogorov construction, whatever. Same thing. Okay. So one, instead of positive linear functional, we are using the CP map and using this property. We have to get an inner product. We have to get we got the right kernel. Right? The kernel is this, right? Usually for GNS, we will take B of H itself. Here we are taking B of H times H1 something. We need to. Okay. Because T of whatever X1 star X1 will going to map inside the algebra, right? It will land up in an algebra, right? That is what is a Hilbert module property. If you don't have that, then that will be what is called Hilbert module. Phi linear functional is something taking, it's a CP map. A positive linear functional CP map taking values in C.
Yeah.
Okay.
So like
if the range is finite dimensional, then it is CP. Okay. The positive map will be CP. Right. I think so.
Fine.
Huh? No.
No, like in finite dimension case, you do have maps which are positive.
Correct. That's not true. Sorry. That's not true. Yeah. So, but the range is C, I think range is commutative, then it is true.
Okay.
The range is commutative. For C, it is true. The positive linear functional is CP. You can treat C as an algebra. Yeah. It's an algebra, of course. It's a field, in fact. So, yeah. So that will be CP. Okay. And the GNS, this construction is same as the GNS construction for that. Okay. So you just don't take other things. Can't forget about those YIs. Just to take T of X star Y.
Yeah. So when inner product takes
values in an algebra, that is called a Hilbert module. Okay. So you will get an Hilbert module. So we want Hilbert space here. We are working with concrete Hilbert space. Okay? Such that this lambda of xu is total in H. Okay. And 2 lambda xu, u going to lambda xu is linear in both the variables. Is bilinear, whatever. Is linear in both the variables. 3. What are the other properties? Yes. No, it's true, but it's true. But we'll come to that. Okay. Yeah, the inner product property. Okay.
Yeah.
The inner product. So this is just, let me write it and then show it to you. Lambda of x1 u1, and then you take the inner product, the Hilbert space inner product, lambda of x2 u2, that is going to be given by the kernel. So which is just going to be u1 t x star x1 star x2 u2, right? Okay. So yeah, and okay, but we may not have time to finish it. I will recall it again. So we will just finish this proof, okay, and then stop. It's actually unique. I mean, this Kelvin pair is unique, no?
Yeah,
that is unique up to some minimality condition. These lambdas, whatever this lambda, these lambda vectors, these vectors should be total.
Yeah.
So up to that, it is unique. Okay. So that uniqueness condition is there. That's one thing. And I mean, actually the kernel we are going to use is that one, but we will make y to be the y part to be identity.
Oh,
It doesn't matter. See, the point is this proof. The point is you define, so you get a Hilbert space. Okay. You have K from B of H1 tensor B of the earlier K, okay, B of H2 tensor H1. Okay. You have a from, I mean, this cross this. You have a positive differential kernel. So you get H. Okay, let H and lambda be the Helm-Gelfand pair. Okay. So then maybe lambda not be the Gelfand pair. Okay. Okay. Then you define lambda of just, we just want the lambda. Okay. Lambda. So it's the same. Hilbert space is the same. We define lambda of xu equal to lambda naught of x1u.
you take the closure with respect.
And then this itself is total. The point is what you have to need is lambda naught xyu is actually equal to lambda naught x1 yu. It's clear. That's because you take the difference, lambda naught xyu, okay, minus lambda naught x1u.
So, but U is in H1,
Yeah, H1, right?
but and Y is in B of H2.
That's right. So I have to take the H2, I think.
Yeah, you have to take H2 only there, because even D is a map from H1 to H2.
That's right, that's right.
So
Yeah,
B of X star X will be in B of H2.
that's right. This is because yeah.
Yeah, like U has to.
No, it is H1 only. T comes from H1. Yeah, the whatever is not that, that is H2. No, it is H2, right? I'm written H1 tensor H1. Here H1 and H2 are interchanged. It's right. H1, T is in H. Oh, there it should be H2. I'm sorry. Here it should be H2, right?
In the above.
Yeah. That is why. That's all. Here it is H2.
Yeah, like when there, the inner product.
Yes. The original one is, yeah, B of H1 tensor B of H2 tensor H1. Okay. Here it is H2. Y1U, then there also it is H2. Oh yeah, there also it is H2 only. Sorry. Did I write here H1? Yeah, here it is H2. That's why here it is H2. Here it is H1. It's H2 because we are acting Y on that.
Yeah.
So this is also H2. I'm sorry. Sorry. Yeah, this is also H2. I'm sorry. Yeah, this is also H2. Yeah, now it makes sense. So this is H2. Yeah, I have written it H2 here, but anyway, it's okay. Yeah. Yeah. Now you take the inner product with any other. I mean, any other lambda x prime, y prime, u prime. Okay. I mean, you can't actually, you don't know what is lambda not x, y, u concretely, but you know the inner products, right? You can take the first inner product and second inner product, that will be the same thing, right? I mean, sorry, here I have to use yu. Sorry. You take the inner, this inner product will be kernel given by x, y, whatever that will be some inner. You write that inner product. Okay.
And that will be easy.
That will be precisely same as when you take the inner product with the next one.
Okay.
Whether y comes separately like that or y comes with u and identity, that doesn't matter. Right? In the kernel definition, right? Kernel is this. Kernel, what is a kernel? So
it will be 0.
Yeah, that's what I'm saying. Kernel is U2 T of X1 star X2 Y1 star Y2 U1, right? So sorry, here U2. This is U1. Okay. Now you can bring this is equal to Y1 U1. Okay. T of X1 star X2 Y2 U2. I mean, this is okay. Now this is same as you get, I mean, you can forget about the y part. You take y to be 1 and take the number. Or you can keep the y there and not here. Okay.
Yeah.
Okay, one of them. So since those sets are total, if something is orthogonal to total set of vectors, that is that is actually 0. So they are equal. So this is the same trick we have to repeat for each and every statement. Okay. So this is total is one thing. Second thing is, of course, this is third one is clear. That's direct. By taking one, it is direct. And the second one, linearity also, you have to take that minus alpha plus, I mean, alpha x1 plus beta x2 you can take. And then you can take the alpha and beta out. Okay. Then take the inner product with total set of vectors. Right? And that will be the same thing. It's clear. I don't have to write it. It's the same thing, right? It's clear. Similarly, you do for alpha u1 plus alpha u2. You take it out that. So it will be clear that that's linear. Okay. So it will be, I mean, you take the inner product with it. So they are same vectors. Okay. So it's linear. That map is linear. And so linearity and this is true. Okay. And for the isometry part, we need the unital. See, you can define a V0. So this has to be somewhere here. There exists an isometry V0 from H1, right? H1 to H, which is U going to lambda 1U. I mean, you take both X and Y identity. And this is an isometry is clear, right? It satisfies that inner product, the previous inner product condition, right? Look at that inner product. You take X1 equal to X2 equal to 1. Then lambda 1 U1, lambda 1 U is U1. T of 1 has to be 1. Okay. It's unital if, I mean, we don't assume unital for all the case, but when specific, I mean, whenever the specific requirements are there, we'll write it. Okay, if T of 1 is 1.
T of H1 is unital.
Yeah. See, for our whatever the channel we are using, there T is not unital. It's just the dual map is unital. Okay, symplectic channel they need not be unital.
No, but like we need B of H1, like we're using 1 here, right?
Yeah.
In B of H1, and
Right.
that is always there. Like B of H1 is unital.
B of H1 has a unit, you are saying.
Yeah.
B of H1 always have 1.
Yeah. So like, why do we need like what do you? Oh, T of 1
T
is
of
equal
1
to-
is 1.
Oh yeah, that we needed to be
Yeah.
like normalized. Yeah.
When you, for example, when you amplify with a state tensor, then that is not a unital map, right?
Yeah.
Okay.
I just assume T of 1 is.
Yeah. So, I mean, sometimes this partial trace is defined on trace class operator. It's not defined on all
Yeah.
operators. Okay. So that is what is the dual map on the state. This is the pre-dual map. This is that is the pre-dual map. This is the dual map. Sorry. Okay. If this is positive, that is positive. So we will remember whether we need these unital conditions or not. Okay, we will just keep it here. So this is an isometry, that is clear. Okay. And the uniqueness is clear. If there is another thing, I will invoke whenever we need. Okay. The uniqueness is if there exists another Hilbert space where you have another map lambda prime XU like this, and if that is also total, then you can, I mean, you know that you can write it. This preserves the inner product. You know that lemma, standard lemma. Okay. Then there is a unitary like that. So that's always there. Okay. So yeah, I have 5 more minutes. I want to define a homomorphism. Okay. So this is a propositional element, right? Homomorphism from there. I want to define a map pi from B of H1 to B of H. There exists a homomorphism from B of H1 to B of H. Okay. Such that pi of any x acting on any vector. This is a total set of vectors, right? Lambda, this is maybe x naught acting on lambda xu. It's just left multiplication. That's why I'm saying this is just GNS. Okay?
Yeah.
It is just lambda of. So,
This is the representation.
Yeah. This is a representation we want to define. Okay, we want to show it's a representation. Okay. So there exists a homomorphism. Okay. This is pi from B of H1 to B of H, such that pi of x naught acting on maybe x prime u equal to x prime. Oh, this is comma. What I wrote is not 1, it's comma. X prime. Okay. Okay. So what we do is the following proposed proof. Let u in B of H1 be unitary. First, we verify this for unitary. Basically, left multiply it, verify this is unitary. It preserves inner product. Okay. Then you define pi of u acting on lambda x prime comma u to be equal to lambda of u x prime u. Okay, you define. So you verify that whether it is a unitary. Okay, so we want to see this lambda of u. So we may have two. We want to verify this pi of u lambda of x1 prime u1. Okay, pi of u acting on lambda x2 prime u2. Right. This is equal to by definition lambda of u x1 prime u1 lambda of u x2 prime u2. Now that is going to be, there is no y part, so it should be y1 here. And as you know, I mean, we have already calculated all these things. T of x1 prime star u star and u x2 prime. This is what you'll get. U2. This is what you'll get, right? But u1 star u2, u star u is 1. So this is going to be u1 t of x1 prime star x2 prime u2. Now this is equal to, because this is precisely lambda of exactly x1 prime u1 lambda x2 prime u2. So this implies pi of u extends to unitary. Pi of u preserves the inner product and the total set extends to unitary. On H. Okay. Okay. And it's clear, it is just the left multiplication. You are just multiplying, you are taking the u inside and multiply the x1 by u. So it's clear that pi of u1 applied with pi of u2 is same as, of course, they are unitary. They are all group. It's well defined for unitary. So this is true for all u1 and u2. Okay. Now we want to define for any operator. We want to take linear combination. We know that anything in a C-star algebra can return as
Unitary span of unitary.
one of 4 unitaries.
4.
Yeah. So if you take any operator, if any C-star algebra is enough, but let us work with B of H, B of H1, and X is self-adjoint. And of course, any operator is span of 2 self-adjoint operators. And we can divide it by norm and get it as a contraction if you want. Okay, less than or equal to 1. Then self-adjoint, so spectral theorem can be applied. Okay, then you can write x to be as x half x plus square root of 1 minus x square, right? I times square root of 1 minus x square plus x minus I into square root of 1 minus x square. Okay. This is the cosine. If you want, theta of x is to be cos inverse of x. I mean, the spectrum is contained in -1 to 1. You have the cos inverse function. Okay, that function will give you an operator. Okay, you can apply the operator. So you get this cos inverse. We have done it for unbounded operators, even all these functional calculus. So we have this operator. Then this x is nothing but half of e power I theta plus e power minus I theta. That's all. Okay. Same thing. Same thing. Okay. So anything can be written. So we want to verify for, so let x is equal to summation. We need 4 unitaries. Let's take some lambda I ui. Okay. The lambda i's are scalars. There is a lag between what I write and the screen. Here itself I see the lag. I don't know. When it is connected, it becomes, or the pen has, it dropped it once. lambda I in C and oops, not that, UI unitary. See, I can't see what I'm writing. Unitary. See, I can see what after some time only I can see what I'm writing. Okay, it's unitary. Okay. Now we want to see that. So now we can define pi of x to be pi of x acting on lambda of x prime u to be equal to, we can just write it as, I mean, you can just take it inside summation. It's linear. You can keep it out or it doesn't matter. Lambda is linear. I equal to 1 to, I keep it out. Doesn't matter. Summation lambda of x, sorry. Lambda, I'll change it to Ci. Ci Uy x. Okay. Now first I have to see whether it is well defined. If it is well defined, then we can define it like this. Then it is just left to multiplication. It is clear it's a homomorphism, right? So we have defined it in all. You don't have to worry about extending something because algebra is a finite linear combination of unitaries. If you see, there is a difference. If you have a projection, I mean, usually a Van algebra or even B of H, projection will generate that. But then projection, you have to take the closure. But here, for unitaries, you don't need to take it. It's just linear span of unitary. So you just have to define it and you just have to check whether it is well defined. That's all. So is it well defined? So if x is equal to summation Ci Ui equal to summation di Vi, okay, then we don't have to, I mean, because it's linear, we have to verify it's 0. Okay. If it is 0, the range should be 0. That's what we have to do. Yeah. Okay. So suppose summation Ci Ui equals 0, then we have to say that pi of that is also 0. That's what we have to verify. Then pi of summation Ci Ui. Okay. So we take, to prove that that's a vector, lambda is a vector, we take inner product with the total set of vectors. Okay. Summation Ci. So lambda x prime u, x1 prime u times lambda x2 prime u1 u2. Okay, we take this inner product. We have to show this is 0. That's enough. Okay. Now this is going to be summation lambda, I mean, you keep the summation Ci lambda of ui x1 prime u1 lambda of x2 prime u2 .
It will be 0.
Yeah, how is
Because
it
like
0?
you'll get C1 star outside first.
No, let's compute the norm instead of unitary. Huh? C1?
Like you will be summation of Ci star U1 trace, I mean T of Ui star X2 bar, I mean X2 prime U2, then take Ci star into the second thing, and T is linear, so it becomes Ci Ui whole star. Summation of that.
Ci Ui whole star. Yeah. Ci Ui, yes. Summation Ci Ui you will get. Yeah, that is 0.
If T is linear,
yeah,
and T of 0 will be 0.
Yeah. So that is one way. So the other way is, that's also easier. That's another way is, you don't have to take it inner product with it. Just consider this summation Ci Ui, then take this lambda xu itself. Okay. Norm square. Now you take this inner product. This will also be equal to 0. You do the same thing.
Okay.
Summation, sorry, pi of this. I mean, you take the pi of that, which will go inside like this, right? That will also be 0. You take the inner product, it will be 0. So it's well defined. So we got a homework. Okay. So you'll see more. You'll see the Stein spring in the next class.